Let's continue. In the last class, we have already started this topic to some extent. We have covered to some extent. The topic is overview of design process of embedded system. Okay, if you want to design embedded system, right? How we do it means as soon as you get the idea, otherwise as soon as you get the problem, you jump into designing embedded system, or you sit for some time and make a plan. That's what it is. If you are a beginner and if you were to build embedded system, how would you do it? You have seen similar things in our college. We don't know anything about embedded system. We still made while you are doing the first embedded system. Okay, how was your feeling? You directly construct the embedded system which is functioning one, or in that process you may encounter many difficulties. Sometimes you buy some components and later on you realized you don't later on you realize they are not useful for your project and you drop in the dustbin and so on, right? So if you without any plan, if you try to build embedded system, you will buy components or many things which are useless. It adds cost to your project. Okay, it increases the cost of the project. And also while writing the program also, and while building the circuits also, you bound to do many wrong things. So to avoid all these things, one needs to have some structure for designing the embedded system, and we are talking about such structure here under this topic called overview of design process of embedded system. Okay, see, if you are building embedded system on a large scale, we don't produce all 1000 or 5000 products in the first go. What we do is we build a prototype one, means single one, maybe small one or a big one, or equivalent one. Okay, fully functional one, which is one, and you build it, you test for all inputs and see whether you are getting the desired outputs or not. If you feel it is working fine, then only you go for large scale production, right? Next, see, there are many models which are widely used in the industry. Among those models, this is one. It is called, it includes both. It is, if you move from top to bottom, our design process is classified into, or divided into these stages or steps, you may say. These are the steps or stages: requirement stage, specification stage, architecture stage, component stage, system integration stage. Okay, because it is such a complex thing, we divide that complex task into small functions, small tasks. Okay, and these are such tasks: requirements, specifications, architecture, components, system integration. And if you move from requirements to specifications, and then to architecture, and then to components, and finally you integrate all the modules, if you follow this approach, it is called top-down design. Otherwise, sometimes what we do is, it is natural, you may not adopt the same thing throughout the design process. You may have to go to the previous stage or previous step and see everything is functioning correctly there. Sometimes you are in the architecture, you have some doubt in specifications. Otherwise, you have in component stage, and there you've identified some flaws in architecture. Right now you are here, Okay, after completing architecture, right now you are in the component stage. After identifying some problems in the architecture, we go back to the architecture, fix those problems, and then come back to the components. Okay, it is very frequently we may go back and come forward and so on and so on. So it is not perfectly purely strictly a top down design, it is both bottom up design as well. So if you go from requirements towards system integration like this, it is called top down design. And sometimes we go back and correct the flaws in the previous stage and come forward. Okay, it is also backward bottom up design. Okay, it is both, it is blend of top down design as well as bottom up design. Okay, it is very rarely we move from top to bottom. Many times it happens. Okay, many times we need to go to the previous stage and correct the mistakes and go to the next stage and so on and so on. Next one, see, these are the top up design and bottom design we have just now seen. Next few important thing is, while designing the embedded system, you need to keep some goals in mind. Should be very careful at these goals while designing the embedded system, and those goals are mentioned here. One is manufacturing cost, the other one is performance. Performance means the speed at which the device responds, your embedded system responds to the inputs. We want the system to be higher performance, means it should respond to the inputs very faster and produce the output. Next one is power consumption. These are the very important goals one should keep in mind while designing the embedded system. At the end, your embedded system should meet these goals. Okay, we have to design embedded system in such a way that the final product should be able to meet these goals. These are very important goals. If you relax at these goals, you may lose market. That is, you may lose market means you lose money. No point building your embedded system on large scale. It is no more a marketing, it is just a hobby project. Manufacturing cost means we are making one product, embedded product, at the cost of 200 rupees. Other company is making the same product with all the same functionalities with only 170 rupees. Let's say people like to buy their products, not ours. So we have to minimize the cost of the product as better as possible. Otherwise, we unnecessarily lose our market. So this is very important goal if you are making embedded product for business. Next, performance, as we said just now, performance in embedded systems always refers to speed. Okay, means you have to design embedded system which is faster. It takes the input and without any delay it should able to produce the output. Next, power consumption, and it is also one of the important characteristic or criteria one should keep in mind. Finally, the embedded system product should meet this power consumption. Now, why power consumption is such a big thing? Most of the embedded systems are portable embedded systems, means you can carry them from one place to another place. They are small in size, less in weight. That's why we can carry them from one place to another. If they are portable, then how about the power supply? Or do they use 230 AC mains power supply or a battery power supply? They will use battery power supply. And what is the amount of energy which can be stored in the battery power supply? it is not that great. So you must build embedded system which consumes very little power from the battery, so that battery comes for long time, many days. That is the power consumption. So we have to make embedded system so that it consumes very little power from the battery available power supply. And these are the main goals one should keep in mind throughout the design process. Next, we will elaborate all the steps which were shown in the previous block diagram. Let's move on to the next slide. Next one. So the first stage in the top-down model or bottom-up model is requirements. Now, what are the requirements that are needed or that are necessary? What are the requirements of embedded system? These are shown here. Performance. As we said just now, performance means the speed at which the device responds to the inputs. Okay, it needs to be very fast. In some embedded systems, even there is a small delay, it is not allowed. In some other embedded systems, it is okay, but in specific systems where speed is critical, then you meet speed. There is no other, there is no relaxation here. For example, airbag opening system in car, automobiles, airbag opening. As soon as the car hits with hits any wall or something, the airbag should open immediately in no time, right? If there is any delay, then it is not allowed. It causes human loss and so on. So there are cases where speed is critical, the ultimate. In other areas, speed is not that much important, although speed is the highest concern here. Performance means speed. Next, cost. Just now we said cost, you have to make embedded system product so that it is less cost. You have to reduce the cost as much as possible. So cost here means there are two costs. Okay, one is manufacturing cost, the other one is non-recurring engineering cost. It is called NRE cost. Our cost is of two aspects here. One is manufacturing cost. For example, you are building some embedded system project. Manufacturing cost means the cost or the money that you spend on components. Means you spend 300 rupees on Arduino board and 100 rupees on one sensor, one more 100 on another sensor. Totally you spend 1000 rupees on just components. That is what is this manufacturing cost. Just buying components doesn't make the embedded system. You have to sit and build, you have to sit and assemble the components in certain way. Only then the final product will functions. Otherwise it won't function, right? Now you need some learned person for that. Means who has knowledge in embedded system only can do these things. Okay, and he means this non-recurring engineering cost is the money that you spend on person who designed the circuit. You hire one person, one engineer who makes this type of engineering circuits, means embedded system building, and money you give to him. That is what is non-recurring engineering cost. And see, if you are building one item, one product, then in that one product you have all the manufacturing cost for each product. Let's say you are building one product, and for that product you have to buy all the components, and for that circuit design, for that person you have to pay some money. Okay, you have both manufacturing cost as well as non-recurring engineering cost. Now let's say this is prototype. Now you are taking that into large scale production. You are producing the same item 5000 in number. Okay, you are making the same item 5,000. So what we do, for each item of 5,000, you have to buy all the necessary components. You have to buy Arduino boards. How many Arduino boards you need? 5,000 Arduino boards. You need all the sensors, which are 5,000 sensors, and so on, so on. What about the circuit design? Circuit, do you need separate circuit for all the 5,000 products? Not necessary. Just with the same circuit, you can build all the 5,000 products. So manufacturing cost repeats with every product, whereas non-recurring engineering cost means it happens only one time. You have to give money for the prototype design or for the one product design. You don't need to give money for each product circuit design. Okay, that's why it is called non-recurring engineering cost. So the final product cost includes manufacturing cost and also the non-recurring engineering cost. It is sum of these two. Next, physical size and weight. And we have to think about physical size and weight. Physical size means how big your embedded system is and how much weight it weighs. So there are two types of embedded systems. One type of embedded systems, one is industry use, other one is portable. In industry, in industry we use embedded systems in assembly lines which are very big in size and also weigh around 1,000 kilograms or 500 kilograms and so on, so on. There we don't much worry about its size and weight because they are big in size. So when you are making embedded system for industry purpose, you don't have to much worry about its size and weight. You can place it somewhere and they use AC power. Okay. Whereas if you are building portable device, portable embedded system, portable means which can be carried very easily without much strain, right? So if you have to build embedded system so that they can be fit into small bag, means there is restriction in its size and shape also, and weight. We cannot carry huge weights in a bag on a shoulder. So there is so much concern about physical size and its shape and also on its weight. This is another aspect in the requirements. So we have to build embedded systems according to these requirements. We would be knowing for what purpose, for what application we are building embedded systems. Next, power consumption. It is the same thing, power consumption. If it is a portable embedded system, as we said just now, it operates with battery, portable battery. So that is small battery. You have to make circuits in such a way that they consume very little power. And if it is a industry application, then we don't need to concern much about this power. Anyway, they are fixed at one place. Even they are moving, they will get power from the AC supply, AC grid. Next, markup. Markup means it is like markup test we usually take up in the end exams. Before end exams, we have some type of mock test, means a test before we take up the actual end exam. Means generally what we do is we don't build all the 5,000 products in the first go. We just build one. If it meets all the requirements, all the criteria, all the specifications, only then we bring it to the production level. Okay, not before that. So markup test means it is a test carried out on the prototype that we have built. So this markup test gives idea of how this system functions, how it responds, how it can be used for the customer, okay, by the customer. Let me read out what is written here. The markup may use canned data. Canned means the data which is stored already. Means generally if you use this embedded system in real time, it takes the real time inputs and responds. Whereas if it is a markup model or prototype model, we give inputs which are already stored and see how better it responds to those inputs. Means predefined inputs. Canned data means literally it is stored data. Restricted demonstrations, and it may be executed on a PC or workstation. It is not really taken to field where it will be used. Generally, this test is carried out on a PC, personal computer. This markup model may be a software model or hardware model. If it is a software model, it is generally tested on a PC or a workstation, but it should give customer a good idea of how the system will be used and how the user can react to it. Physical non-functional models of devices can also give customers a better idea of characteristics such as size and weight. Physical non-functional means something like shape. Finally, your product will be like this, like that, and so on, so on. It is prototype. Prototype may be a functional one. Most of the time it needs to be functional, otherwise non-functional. Next, now we have arrived at second stage or second step in the design process, which is specifications. Now what are the specifications? Specifications means specifications comes from the customer. We have to make product according to customers' requirements. Those requirements are nothing but the specifications. Customer says, I want embedded system so that when temperature goes above 40 degrees centigrade, it has to give this type of behavior. When it is 30 degrees, if the temperature is below 30 degrees, it should give this behavior like that. Okay. Now we have to approach the customer, and these specifications comes from the customer. Requirements of the customer is nothing but the specifications. Okay. We have to make this embedded system finally to meet all these specifications as demanded by the customer. The specification is more precise, means it is not something like abstract. It needs to be more precise. It serves as contract between customer and the architect. The person who makes the embedded system, he goes to the customer or customer comes to him and explains all the requirements, all his or her requirements to the architect. Architect means the person who builds the embedded system. Okay, the one who is building embedded system, he should be knowing all the specifications. Otherwise, without knowing these things, he cannot do anything. He cannot make any design. The specification should be understandable enough so that someone can verify that it meets system requirements and overall expectations of the customer. So we have to write down all the specifications somewhere so that when the final product is completed or while the design is going on, you can repeatedly verify whether the design is going to meet all the requirements or not, all the specifications or not. So we have to pay special attention on specifications. Specifications means just requirements of the customer. So we write all the specifications at one place. We constantly have a look at these specifications while at the designing level and also after completion of the product. Okay. So while at the designing level, whole design is made as per the specifications, and after the design is completed, we verify the design whether it is satisfying all the specifications which were mentioned. Okay, for that purpose we write all the specifications at one place. It should also be unambiguous. The specification must be carefully written so that it accurately reflects the customer's requirements and does so in a way that can be clearly followed during design. So we look at specifications while designing the embedded system and also after completion of design. While designing embedded system, we constantly make changes to the design so that specifications are met, or if you think your design is correct, after design is completed, we again test your design for specifications. Next, architecture. In the previous stage, in the specifications means the final design should deliver the mentioned requirements. That's what specification says. Specification cannot say or will not say how your design should be in order to meet the specifications. It won't say that. What it says is, these are my specifications, these are my requirements, you do whatever you can, but finally the design should satisfy all these criteria. Okay, now architecture. Now what is going to do, what is this architectural design means? What we do in this stage is the following. So according to the specifications mentioned written in the previous stage, we start out our design according to those specifications. Means we start out design means we write down, we on the paper or by using computer software, we try to build the circuits or programs. That's what we do in the architecture and architecture design. Means we build circuits. That's what architecture design is. Means how the connection should be in order to meet all the specifications which were mentioned in the previous stage. The specifications does not say how the system does things, only what the system does. Describing how the system implements those functions is the purpose of architecture. Otherwise, you think in terms of blocks here. I want this block, that block, this block, and so on, so on. How they are connected, how they should be connected in order to deliver the final goal. Means all the specifications, all the requirements, and so on, so on. In the architecture design, we think in terms of modules or functions or blocks. I want this block, that block, and how they should be connected in order to deliver or in order to meet all the specifications. Next, designing hardware and software components. After thinking in terms of blocks or modules level, now we start out building those modules in the component in the hardware and software designs. As we said in the beginning of this course, embedded system is not just hardware, not just software. It is combination of both hardware and software. Now embedded system is hardware and also software. So we start out designing software programs and also hardware blocks. So in this stage called design hardware and software component stage, we try to build the modules or sub functional blocks. Modules means it is not the complete program, it is small programs. We break down that big program into small programs here, which are called sub programs or sub modules or modules or blocks if it is hardware. Okay, all those things. So we work out all these hardware and software components in this stage. And what are the hardware components? Hardware components may be FPGAs, FPGA boards, or there may be some modules like we have used some modules in our embedded projects like GPS module, LCD modules, and many modules. Okay, we connect all these things. We work at module level or block level. So in this test, we simultaneously work on hardware section and also software section. It is generally adopted in the industry. It is not that one person builds both hardware and software, and also not one person will be building the whole hardware or the whole software. It is not like so. The whole task is subdivided into modules or blocks or submodules and so on. Each module is given to one group of people. There may be 10 or 15 groups working on the same project. So each one small module is given to one group. Like that, you can parallelly complete all the modules so that you can develop the whole embedded system design in less time than otherwise. If one person has to do all these things, it takes a lot of time. It may take few months or a few years. If 100 groups are working on the same project and the work is divided into sub modules or tasks, where each task is given to one group, so that the whole project can be completed in 2 months or 3 months time instead of 2 years or 3 years. That is the beauty of dividing all these things. And also there is one more advantage of dividing this main program into sub modules. Okay, the beauty is this: if there is finally the project is built and at the end you realize that there are some errors. So if you have made the whole project into sub modules, then you can find out the error and correcting it becomes easy. Otherwise it is difficult to point out the error and also correct it. Next, system integration. This is the last stage in the design process. In the previous stage, what we have done, we have broke down our whole task into several subtasks called modules or blocks. After working at blocks level or module level, what we do is at the end what we have to do, we have to connect all these blocks which were completed in the previous stage together. We have to put all these modules together so that you will get nice functioning embedded system. Okay, the system integration means putting all the embedded sub modules together. Okay, that is what is system integration. And now you get the embedded system. Now what we do is we will put it to test whether the build system is satisfying all the specifications, satisfying all the